Hi guys, so in this video we'll be going over chapter 1.3 of chapter 1 data representation. So this is chapter 1.3 and 1.3 continued. It will be a shorter chapter compared to the last one, but it is still a bit longer than the usual short chapters we'll have later. So we'll be again going point by point with the notes, and we have the book for, I don't know, the book is for reference, I guess, but we'll mainly be using the notes only. So let's start with point one. Understand how data is measured. And they are saying you need to include in your knowledge what is a bit, what is nibble, what is byte, what is kibibyte, mebibyte, gigabyte, tbbyte, pbbyte, and exabyte. So let us look at the notes. So at first, what is a bit? Bit is a digit. A binary digit is referred to as a bit, so either 0 or 1. And 8 bits is a byte. So 8 binary bits is a byte. So here there are 4 bits. Let's assume, right? 1, 0, then 1, 1. This is 2 and 4, but imagine there is 1, 1, 1. So these are 4 bits. And if you get another 4, it will be a byte. And then a nibble. 4 bits is a nibble. The nibble is generally not used that much, but it does come in, question papers. What is a nibble? So yeah, it is half a byte or 8 bits, or sorry, 4 bits. So byte is used to measure memory size. Memory being, system memory or RAM, or storage, even like storage memory, hard drive, and SSDs. And now IECB systems, most common. So this is the measure of memory in increasing orders of magnitude, more or less. Not exactly increasing, you know, in magnitude, like it's no, it is probably increasing magnitude, yeah. It doesn't really matter. So it's starts with 1 kilobyte, but before that we have, byte. So we should look at it on a blank page. So what is a byte? 8 bits, or let's say 1 0 1 1, then 0 0 1 1. This is 1 byte. And then what is a kibibyte? Kibibyte is 1024 bytes. So 1024 individual bytes into, so 1024 of these numbers. So take this number and 1024 of these numbers. Or you could also write it as, 2 to the power of 10. But you shouldn't really, try to memorize that. Then there comes the mebibyte. Mebibyte is basically 1024 KITB bytes. So this thing, right? Take this whole thing and into 1024. So, and it increases and increases. So this is mebibyte. If you want to go gigabyte, so gigabytes, or what, if you commonly know it as, but gigabyte is different here. But we'll look at why gigabyte is different than gigabyte or mebibyte, whatever. So this is mebibyte, this whole thing, MIBI. Now, what if you want to go to gigabytes, GIBI? So if you want to go to GIBI, you need to multiply it by 1024 once more. So 1024 once more, and now we have gigabyte. And then if you go one step higher to TB byte, you can multiply it again by 1024. So this is the common thing you need to know. 1024. This is the number you need to know. So kilobyte, 2 to the power of 10, you can, put in a calculator. What is 2 to the power of 10? 1024 bytes. And then what is one megabyte? 1024 bytes into 1024 bytes. So that would become, 1,048,576 bytes. And you do not need to memorize these millions and billions of bytes. You only need to memorize this thing. KB byte, BB byte, then GB byte, then TB byte and PB byte. So it's a bit hard to pronounce or whatever, but these ones are easier. So you can, remember these ones. And then after you remember these ones, you just have to, understand that these ones are a bit different. Or, these ones start with 1000 and this one start with 1024. So yeah, you just remember kilobyte, megabyte, gigabyte, right? And then only remember that instead of multiplying it 1000, you multiply it 1024. You do not need to remember PB byte exactly as it is. So what is a kilobyte? So it is 1000 bytes and 24 less than, KB bytes. So it is only 24 less, but as we increase in number, as you can see, there are 48,000 more bytes, and there are those bytes are missing here. They are not here. So it starts off with 24, but once you go to MB byte, it becomes 48,000 less, and at PB byte or yeah, PB byte is much more bigger than a petabyte by like, I don't know, 100 billion ish. Yeah, 100 billion ish or something like that. It's much bigger. And the base here is to the power 15, and here the base is 10. And I was wrong before, so this is increasing by 10 orders of magnitude or 10 zeros at once, and this is increasing by 3 zeros. But the base is different, so the increasing in order of magnitude does not really matter. So yeah, in short, you need to memorize this. What is a kilobyte, megabyte, gigabyte? And then you can just make an analogy to this thing. So this is how files are stored, and normally normally we use in marketing, or let's just say you were going to buy a product that was tech related or had any kind of memory. Your memory would be probably marketed in this form, which is kilobytes, megabytes, with let's just say whole numbers, or sorry, standard, I don't know. So basically zero at the end. But normally inside of a computer we use this. So if a computer is adding two numbers, dividing two numbers or something like that, it can highest hold up to these values. So 2 to the power of something value. So you can think of it as like this. This one is used for simplicity, and this one is the used for practicality. Now, file calculation. So file calculation is a wrong word. You need to only calculate the size of a photo or an image. So an image file, not any file, an image file. So the file size of an image is calculated as image resolution in pixels into color depth. Okay, so calculate the file size of an image file and the sound file. Okay, so sound file is also included using the given information. Calculations must use the measurement of 1024 and not 1000. So let's look at a example. Let's assume a question is given and they have said there is a photo or an image of 1000 by 800 pixels. So this is an image of, let's just say, a triangle with a circle behind it or circle to the right side. So this is an image, and they have said calculate the file size. So they have given the image resolution, and they have said this is a 2-bit depth. 2-bit depth image. And how do you calculate the file size? You take the resolution, so 800 into 10, 1000, 800,000. So this is the number of pixels you have. What is bit depth? So number of bits used to store 1 pixel. So 1 pixel can store 2 bits of color information. So 1 pixel can store 2 bits of color information. And 2 bits would be like this: 1, 0 or 0, 0. So how many colors can you store? So this is 1 and this is 2. So 1 plus 2, 3. Maximum you can store 3 colors. So how many? So 0, 0, 0, 1, then 1, 0, then 0, 1, 1. So these are the 4 colors actually. So 0, 0 is a color also, if you think about it. But in decimal numbers, you can only store up to the integer 3. So 2, 1, 0. So 0, 1, 2, 3. These 4 numbers you can store. So if you have 2 bits or of bit depth, you can store 4 colors, 4 individual colors. And so this is your bit depth, and you multiply the bit depth with the what is this? Image number of pixels. So image resolution is 800 by 1000, and so you take the image resolution, multiply the vertical and the horizontal columns or number of pixels, and you get 800,000. So this is what is this? After you multiply, what do you get? You get bits, number of bits used to store this image, right? The individual number of bits. If 1 pixel takes 2 bits, right? 1 pixel is 2 bits. What would be 800,000 pixels? 2 into 800,000. So now we can bring out the calculator. We can bring out the calculator. So this is in bits, right? The answer will ask you to give your answer in MB. MB, MIBI bits, MIBI. MIBI. If it says MB, short B, then it might be megabytes. But if it says MB, it will be probably, MIBI bits. So my bad, not the date. We use the calculator. Take out your calculator, and so 800k into 2. This is the number of bits, 1600,000. So number of bits, now we divide this by 1024. So this is the first division, we get kilobits. So 1000 kilobits and divided by again 1024. Now we are at MIBI bits, MIBI. This will be your answer, 1.5, 1.53 MIBI bits. You can throw out the rest of the decimals. And this is generally how you do the calculation. And for file size of, let's just say, any kind of sound, you take the sample rate, number of samples per second, right? The number of samples, it will be a whole number or integer number, right? So 300. And the sample resolution in bits. So again, like pixels, pixel has no unit, no nothing. Pixel is just the amount of information, or the amount of, let's just say, pens you are buying. And the sample resolution is the bit depth, or the amount of money you are paying, the cost of the storing so much pixels. So if you think about it this way, then you can remember it easily. One thing is the thing you are storing or buying, right? The object you are storing or buying, that would be the sound sample rate, right? This is the thing you are storing. And in terms of image, you are storing pixels. So this is the thing you are storing and buying. And what are you using? So in terms of image, you are using the bit depth to store the image. And when it comes to sound, you are using the sample resolution. So the number of bits. And in terms of sound, there is a temporal aspect. What is the meaning of temporal aspect? So time is involved. The file size is increasing over time. If you think about an image, the image is a still image. It is not a video file. If it was a video file, then you would need to calculate multiple image, uh, how should I say, multiple image sizes, right? Image file sizes. But it is a still image, so you do not need to make multiple calculations. So here, this is a sound file, so you need to make multiple calculations. But let's just say sound file, the sample rate and the sample resolution does not vary, does not change. So you do not need to make multiple calculations. You just need to multiply it by one extra number, which is the length of your sound clip or sound file. So this is the temporal aspect. And yeah, this is generally how you do it. The sound length will be in seconds, as you can see, and the sample rate might come in hertz, right? Might come in hertz. What is hertz? So it is the number of samples each second. So if the question says 400 Hz, that would mean 1 second equals to 400 samples. Yeah, so this is basically it. And then sample resolution will be again in bits, so 24. So 400 into 24, then let's just say second was 10, so something like that, and you get a big number. Then you divide that by 1024, right? 1024 to get kilobits or kbps, if you will. Kbps, then you can divide it again to get mbps if your answer says to give it in mbps. Okay, so this is all calculation. Let's move to the next topic. Understand the purpose of and need of data compression. Compression exists to reduce the size of file. The impact of this is less bandwidth required, less storage space required, shorter transmission time. Okay, file types. So musical instrument digital format or MIDI. MIDI file user stores music. Uh, Communications protocol that allows electronic music instruments to interact with each other. Stored as a series of demand but no actual notes. Uses 8-bit serial transmission, asynchronous. Each MIDI command has a sequence of bytes. So way too much information. Yeah, this much is not needed. So stores music files, sure, and communication protocol that allows music instruments to talk with each other, sure. This too, you can keep this too in mind, and you can also keep this in your mind if you want. But this one is a 50-50 hit or miss. This might come like very, very rare once in, I don't know, 5 years, 10 years, whatever. But you just need to know that this file only stores the instructions itself, right? There is no actual music notes. And one more thing is this is lossless. This is not a lossy format to store files. This is a lossless format. And one more thing is a lot of storage. So what you do not need to know or is probably useless in these things. So yeah, these ones are not needed. You can obviously read it, understand it, but no need to memorize if you are doing that. Now, next up is MP3. It uses technology known as audio compression to convert music and other sounds into MP3 file format. So it is compressed. The compression reduces the normal file size by 90%. Then using file compression methods, which uses perpetual music sharpening. So you do need to memorize this thing, perpetual music sharpening. How is MP3 compressed? With the use of perceptual music sharpening. I was pronouncing it wrong, my bad. So use of perceptual music sharpening. Remove sounds that the human ear cannot hear properly. Certain sounds are removed without affecting the quality too much. So all these 3 points, please do remember them. At the very highest, right? There will be questions with 2 marks. So you need to know 2 points. So you need to know 2 points. So I think you should remember three. Why? So how does it work? Or how does it work? It uses perceptual music sharpening. So it is generally how the file is compressed, right? But how does it remove the data, right? How does it compress the file, or how does it save storage? It saves storage by removing sound that ears cannot see, and these sounds do not affect the quality too much. So I think you should remember all three, because these two are a bit different than this one. But I think if you write any of the two, you will always get 2 marks. But better safe than sorry. So next, CD files are converted using file conversion software. Okay, cool. Use lossy format as the original file is lost following the compression algorithm. So MP3, right? MP3 uses lossy format as the original file is lost after no, during compression. So MP3 is lossy compression, uses perceptual music sharpening. So next up is MP4. This format allows the storage of multimedia files rather than just sound. So music, videos, photos, animations can be stored. Anything, honestly. Videos could be streamed without losing any real discernible quality. So MP4 is basically this, nothing major. It is also, compressed. It is lossy. It is not lossless. And next we have JPEG. So JPEG is a file format used to reduce the size of photographs. Reducing picture resolution is changing the number of pixels per centimeter. So, okay, cool, but this does not really relate to JPEG. I don't know why they put it in here. When the photo undergoes file compression, the file size is reduced. I mean, sure. JPEG will reduce the raw bitmap image by a factor of between 5 and 15. Again, this is not really important. So, I'll tell you what JPEG is mainly doing. So, human eyes are very sensitive to brightness, so they can, you know, notice a change in brightness much better than the change in color. So, a certain type of red color, right? If you increase or change the brightness enough, you can make it into orange. So, yeah, more or less, brightness is much more important to human eyes. So, what JPEG does is, takes the brightness and keeps it, but then it separates out the color information. So the information of colors, it separates those out and kind of throws out a bunch of color information, which is not very important to the main image. So this is how JPEG compresses a photo. So it keeps the brightness mostly intact and reduces the information of color. And so this is how JPEG works. And it's a image storing file format. So next up is lossy and lossless file compression. Lossless file compression is basically data is not lost, but the file size is reduced. And lossy is file size is reduced, but some of the data is also lost. So all the data bits from the original file are reconstructed again when the file is uncompressed. Important for files where loss of data would be disastrous. In the example here is spreadsheets or text files. An algorithm is used to compress the data. No data is lost. Repeated patterns as text are grouped together in indexes. So lossless, basically, yeah. It is used for, text files. A compression algorithm is used. No data is lost. Repeated patterns are recognized and grouped together in indexes. So you only need to memorize, you know, these points. You can also take this on also. But these 5 points, if you write them in the question paper, you will get marks. So what is run length encoding? So run length encoding is basically this. Repeated characters are converted into, you know, numbers. So let's just say here I have 5 A's, right? 3 plus 2 is 5 A's. So it becomes 0, 5. So 0 will represent A. And so 0 is A, and we have five of those, five of the A characters. So yeah, it basically is compressed down to this 5 A characters and oh my bad. So it is compressed in the sense that uh, 5 characters of 97. So 97 is A, then 4 characters of 98. So 98 is B, then 2 characters of 99, which is C. So A, B, C. So this long thing is converted into a few numbers. And so this is basically run length encoding. So repeated characters are identified and grouped together. So you can read the whole thing if you want, but I'm giving a short explanation that repeated things are identified and put into indexes. So run length encoding is not perfect, and it does not reduce the size of the text if things do not repeat. So as you can see, CD, CD, CD. So the letters are changing. And so if you use run length encoding on this, the file size might even increase, not decrease. So it will either stay the same or increase. So you need to have a lot of repeated information to make run length encoding viable or work. So what is lossy file compression? The file compression algorithm eliminates unlimited data. It's in like MP3 and JPEG. So MP3 reduces or throws away sounds that are outside of the human hearing range, and JPEG reduces a bit of color information and keeps most of the brightness data intact. And it is impossible to get the file back once it is the original file. It is impossible. You need to have the original file to have the whole data set, or you cannot reconstruct it. Reduces the quality. Even though the quality is not noticeable to the normal human, it still is a reduction in quality, more or less. Up next is this image. The I guess in JPEG. I don't know in which file format, but in JPEG, the image resolution and color depth are reduced. So that is more or less all on data storage and compression, and compressions continued. So one thing I guess it did not mention in the notes. Why should we compress things? So we should compress things to reduce size, as if you upload a compressed image, the bandwidth requirements is lower and whatnot. And less storage space require shorter transmission time. So there are a few benefits to compression. And I think that covers all of the topics in chapter 1. And next we'll be going on chapter 2 in future videos. So that is all. Goodbye.